Okay, let's do that. Right. So this is just question number 3. Yeah, so again, we are just solving this section on automorphisms. This is section 2, right? Yeah, so okay, but I just write automorphisms of fields. So this is problem 3, and right. So we are interested in Q automorphisms of, and what is omega here? One. Okay. 120. Okay, so it's just cube root. Okay, cube root of unity. Okay, right. Okay, and the question is, show that the 6 functions given in some example extend to Q automorphism. So what are those functions? Do you know? Oh, should we just look? I'll just look at it. It's here. So yeah. So what is the definition of a Galois extension? Yeah, when the fixed field is the field again. Yes, yes. So they have defined, right? Definition 2.15. So K is Galois over F if the fixed field is again the same thing, right? So that definition is there. Yeah, now you see the field. Okay, let's just look at this for a moment. In fact, the field, this is the field generated by this and this and this of this. Okay, so basically this extension is the splitting field of x cube minus 2. Hmm? And omega satisfies this over q, and omega is not in this. We see that the degree of the extension is 6, right? Now, what does it mean? It means that we need 6 automorphisms. Okay, that is not a theorem so far, but we know it. I mean, you means we know it. It's a fact, right? That the degree of the extension should be equal to the number of automorphisms for a Galois extension. Yes? Yes. Okay, cool. Fine. Right. So it can be shown that the 6 functions. So here they are giving us some 6 functions which are partial functions. Right? They are partial. Yes. Oh, I'm sorry. Yeah, I made a mistake. Ah, I did not change it. Yes. Let me just do this. Okay. Yeah. So it can be shown that these 6 functions extend to distinct automorphisms of this, and thus the Galois group, size of the Galois group is equal to size of the extension. Okay. And so this is Galois. Right, right. So here they are in fact also taking this as the other definition of a Galois extension. That size of the Galois group is equal to size of the is equal to the degree of the extension. That is probably also they have proved earlier. So that's okay. Now the task is to see why these functions can be extended. Correct? Okay. Hmm. So let's take one of them. Let's take one of them. It's an easy exercise. Let's So what have you tried when you tried to extend it? So for example, if we take you take this and then they have this function where they send this, right? Now how will you extend this? Huh? So what should be the function? Yeah, here I should write that this is identity and we are trying to extend this function, right? So there is a function till here. So you have to tell me where can you send omega? Okay. So let's say that yeah, send omega to omega. Okay. Oh yeah. So I'm sorry. I mean, uh, they have already told us that. But then there is a confusion. So why do they say that these functions extend to distinct automorphisms? These are already fully defined, right? These are already full. I mean, yeah. So they. Okay. Okay. I'm sorry. So sorry. Yeah. I think I made a slightly mistake. Yeah. So I just erased this thing. I'm doing something wrong, right? It's like they have given us the function and they are telling us to check that it is an automorphism of the field. Yes. No, no. Yeah, that is the question. But have you checked that these are automorphisms? Okay. So, uh, why is the identity automorphism? That is fine. I don't need to say that. Yeah. But why is so? For example, if I send cube root of 2 to cube root of 2 and then I send omega to omega square, they would have a name for this tau. Yeah. So question is for you, why is tau an automorphism? You would have thought about this. So because it is not means A priori one has to check that it respects the field structure, right? The tau of AB is equal to tau A times tau B and so on. So on an now, of course, tau can be defined on an arbitrary element of the extension using these two things. That is fine, but hmm, you tell me, because this is part of field theory, right? So it comes earlier. So you should have thought about this. Right. I mean, this is the field theory thing that comes earlier. So, anyways, I mean, yeah, so by definition, this, what is the definition of this? Any other definition? Because that is as abstract as it is. I mean, yeah. Okay. Okay, okay. So you are using this recursive definition. Okay, is this the, okay, why is this the definition? Okay, if this is the definition, then what is the definition of this? Hmm? Okay, right. It's a rational polynomial with coefficients in root cube q of root cube root 2. Okay. So is the definition that you gave initially, is that correct? Mm-hmm. Mm-hmm. Yeah. Okay. Why? Okay. Yeah. Right. Okay. That's correct. Good. Good. So that is fine. Yeah. Then that definition is correct. So then you know that. Okay. But then what? How do you solve the problem? So now we understand how it looks like. You've given me two definitions or three definitions. They all have their own advantages. Okay. Now, how do we solve the problem? Where is the, you have to think, where is the problem? Where are you getting stuck in defining, in showing that this is an automorphism? That you have to realize. Where is the problem? Hmm. In defining the images, okay. You are so maybe like omega going to omega square. Okay, see, so the problem when you say in defining omega, the problem here is for us to say why this definition is an automorphism. We don't have to define it. The definition is already given to us. We have to check that it's an automorphism, right? But yes, if you are asking why are we defining it like this, that also has an answer. And that is again something that you know. Think about it. So if you have omega here on this side, and if you have some, now think, if there is some arbitrary field automorphism and you have omega on the left hand side, where can it go? Where can it possibly go? I am coming to your question now, right? In defining omega, you tell me, where can it possibly go? Where is it allowed to go? Let's take F be any field automorphism. Let's say that it goes to some x, okay? Then it implies that x square plus x plus 1 is equal to 0. Is that fine? Ah, so what can x be? You know, omega or omega square. So that's the thing. We have to respect the polynomials that they satisfy, right? Whenever you are taking an element, any element alpha, and you're sending it that side, you have to respect the polynomials, you have to respect the irreducible polynomials, right? If alpha satisfies an irreducible polynomial over Q, then f of alpha should in this case also satisfy the irreducible f of alpha should also satisfy that same irreducible polynomial over Q. So that choice is pretty much sealed. You cannot really change much, right? So that is the thing. So that's very, very clear. Now the question is, among those few options, one choice has been made to us, and we need to show that this actually works. It should work, but so have you thought about this? The reason why I'm asking, because if you tell me what you have thought and where you have got stuck, then that's a better, then I can give a more accurate explanation. Because otherwise, I can tell you something which I think which will be correct, maybe fine, but you have to know how to overcome the difficulty. So let's try it now then. Okay, if maybe it's fine, because maybe when you see this question, it's like, okay, you may ask one question like, why are they defining like this, right? Or how does our arbitrary element? And so I can understand that there are probably many questions that come, and it maybe leads to a confusion, right? But there you have to structure. Okay, you have to one by one. Maybe one thing which you can do is you can write the questions, right? Um, Write the questions and then take one of them and focus on them. Okay. And it shall not be always like this. I mean, once you get clear with the concepts, then a lot of questions will not arise. You see my point, right? Like, how does an arbitrary element look? Maybe it will not arise, because maybe you will realize that in that, but of course, the problems are also going to get difficult. But you will realize that, okay, in this problem, maybe how an arbitrary element looks is not the immediate question, or maybe it's not possible to answer. So you will not. With mathematics, is very important to know what to not to focus on also. right? At one point, it would focus on one thing. So this is how you have to, like, when you do the next questions, similar kind of problems will arise. So you have to overcome them, right, one by one. It's difficult, but that is what you have to do. I mean, that is the challenge. Yeah. Anyways, so let's try to define this. So I'm just writing this again. So while defining this, let's take it in two steps. Sorry. There is actually a theorem which one can use. Is probably they have proved earlier, but still. So here, till here, you see, it is just the identity. So cube root of 2 going to cube root of 2 is an automorphism of this. Fine. That is okay. Yeah. Now the question is that this is now you don't really have to look at the q adjoint cube root of 2. That is just a k now, right? That is just a field. And then you have attached omega. So the question is, why is this an automorphism? So you see this omega satisfies this polynomial x square plus x plus 1. So x square plus x plus 1 is irreducible over, right. But in our case, what do we need to say is exactly q adjoint cube root of 2, because that is important now. That is relevant now. Okay. So, right. Now the situation is like this. Yes, go on. That is fine. Okay. That is correct. But now, how do you explain that omega going to omega square is an automorphism? So now you see you have just k adjoint omega and k adjoint omega, and you have sent omega to another element of the irreducible polynomial, another root of the irreducible polynomial, which also exists. This kind of thing always gives you an automorphism. Okay? This kind of thing always gives. Do you feel that? Are you able to get that intuition? So, what I'm saying is that what the situation is, try to look at because see, even if you look at it here concretely, omega goes to omega square. Why does this extend to an automorphism? Because see, you will of where will you send omega to the power 4? Omega to the power 8. Uh no, omega to the 8, right? Means by the rule, by the how this is a generator, right? We are sending the generator omega to omega square. So everything will get sent accordingly, right? Just give you example. So P of omega will go to P of omega square, correct? Right? And if P of omega is going to P of omega square, then you may say that then though it is a field automorphism by definition, isn't it? I mean, you will send A omega to A omega square. You will send where A can be anything in Q adjoint cube root of 2. And you take anything now. You take omega plus omega cube, you will send it to omega square plus omega to the 6. You see how it is going, right? I'm just using the definition of field automorphism to put the images. Is that fine? I'll just say it in a slightly different way. But there is still a problem, but we have to realize that. You have to realize that. If you don't realize it, then the problem then maybe the proof is incomplete. We'll see. So what I'm just saying is that suppose I have, let's just, okay, this tau, right? Yeah. Maybe I'll not call it tau anymore. I will call this phi because I have fixed the lower field. Suppose I have phi, and now, as you asked, right, how does an arbitrary element of phi look like? So it will, let's say, look like a plus b omega. So where do you plan to send it? Well, I'll send it to, yeah, right, exactly. And phi of omega is omega square. Okay. Then where can the then what do you need to prove now? Everything looks nice, but then where what is there something that we need to prove? Think. Yes. I mean, strictly speaking, something still needs to be proved. But the good news is now we understand the intuitively that it is correct, right? On one level, we understand that this is nice, but what do we still need to prove? Well, we still need to prove because this may not be well defined. This may not be well defined. Why? Because you may have two different elements of this field, or rather, I'm sorry, you may have one element of this field. Let's say, let me call this alpha, okay? But it may have two different representations, right? Alpha may be equal to P1 omega, and alpha may also be equal to P2 omega. Is that possible? Yes, it is possible because two different polynomials can evaluate to same thing at omega, right? You may write it in two different ways. Of course, you might be thinking that if I take these are linearly dependent, it's a basis and so on and so on. You may be thinking in that direction. That is fine, but but it is not enough because there is also a multiplicative structure. Okay, we did not really investigate that. If one also has the multiplicative thing, right? A1 B1 omega, then A2 B2 omega. This will be equal to phi of A1 B1 omega times phi of A. So many things are there, right? So how do you take care of all this? Now the problem is again a problem is emerging. You see, an issue is emerging, so we have to resolve it. Okay. So how do you resolve it? P1 omega and P2 omega, they may have the same expression. Now, how do you prove that P1 omega square is also equal to P2 omega square? So let's write that on the next page. Okay, you understand the problem. Yeah, and yes. Yeah, yeah, okay. Let me write it from scratch. But point is that a good news is you can say that these problems are resolved in a theorem. But let us see it for ourselves and then we can quote the theorem later. Okay. One has to do it like this. You see, I have not done anything so far. I'm just writing what I should write. Anyways, so the point in saying all this is that i- mathematics in general, it should not just be technical, right? You should take a few simple steps, maybe, right? And then, do some simple things and then maybe come up with a problem, obstruction. Okay. If I'm just quoting some lemmas, then maybe it's not so good all the time. But we'll see. So here, maybe I should write omega goes to omega square. So can you tell me what we need to prove? What is the obstruction? Okay. So we need to show. See, we talked about it, that P1 omega equal to P2 omega show P1 omega equal to P2 omega implies P1 omega square equals to P2 omega square. Do you agree with this? Do you agree that we need to show this? This is the problem because we are using two different representations of an element, right? Think when you do group theory, when you have cosets, right? When you define a map from the quotient space, how do you do? Right? You take a coset representative and you define the image. Then you say, we need to check that it is well defined. Right? And then you use either you check or you use some first isomorphism theorem, second isomorphism theorem, or something like that. That is the thing. This is the same thing. This is the same thing. Well definedness, because you are defining a map, you're defining a function, but while defining it, you are referring to certain what do you say? Certain representation, not the mathematical representation, but certain representations of the object. You're representing the object using something, right? You may have pi, but you may represent it in some finite decimal expansion, right? So that's what, and this will be more and more common as you do higher mathematics because things will get more and more abstract. So you will have more and more chances of not being well defined. Okay, so if you when you do more and more higher maths, you see most often the biggest problem will be to check that the map is well defined. Okay, and then some theorems will be invented. You may have to invent it to show that it is well defined. And this is like a toy example for nowadays it's a small example. I suppose long time back it was problematic. Anyways, so we have to show this. So how do you show this? We translate. And by the way, where is P1 and P2? These are in the polynomial ring, right? Is this what you wanted to say? Is correct? Hello? Yeah. Is it correct? This is what you had in mind? Hello? Or is it right? Fine. Okay, good. We need to know where it is. Okay. Yeah. So this is where it is. And then we need to show this. Okay. So how do you show this? Well, it is now you just translate, right? This basically translates to p omega equal to 0 implies p square omega equal to 0. Because you just replace p by p1 minus p2. Okay. And now why is this true? Because they have the same irreducible polynomial, right? Right. Yes. So p omega equal to 0 implies that x square plus x plus 1 divides uh, p, correct? And that implies that omega square, p omega square equal to 0. Okay. So what we have proved is a theorem. And I would have thought that you have read this. And you may have read this. But yeah, reading an abstract theorem may not have may may not have translated into this problem. You may not see the connection directly. But see if you have read this. So suppose now it's good to see a theorem. A theorem now is a relief because I mean every time if you have to do that verification, then it's a problem, right? So it's good to have a theorem. But both are needed. You see, one has to know the theorem, one has to know the proof, but one has to also know small instances of it, right? One has to, I mean, it has to be part of the experience of the person, right? At least an instance of the theorem should be part of part of your experience. And how does it become a part of your experience? When you try, right? When you try, you get stuck, and maybe you overcome, or you overcome somehow, whatever, right? Then you will actually can relate to the theorem. Hmm. So there is this, and there is sigma. Let me just write it for the identity first. And now writing the theorem now is just a formality. Okay. So yeah. So alpha going to write it like, given this, yeah, alpha going to alpha prime is an automorphism, or as one should say, right, generates an automorphism. But soon you will just write is an automorphism. Because the word generate here doesn't really lend any. Once you know that it generates an automorphism, then its value is lost. Then we just use is an automorphism. Okay. Generates an automorphism. Sigma. Of course, fixing generates a k automorphism. I'll just write k automorphism. Yeah, fixing k. If and only if minimum minimal polynomial of alpha over k. Okay, this is just I'm using this notation. Has alpha prime as a root. Is it fine? This is what we have proved. Now I will write a slight generalization, and your task will be to write your proof and send me. Okay? It's not a new theorem, but now it's no longer fixing k, because you see fixing k will not always be enough. If you look at the other automorphisms in that same example, fixing k will not always be enough, because sometimes you are not fixing any of the cube root of 2 or omega, right? So that lemma, so we know we need a stronger lemma, but we can just write it here because the proof is going to be formally the same. Right. This is what the thing is. That's the good advantage of writing things mathematically. If and only if alpha prime is a root of sigma of p alpha x, where p alpha x, or maybe I will let p alpha kx be the and this thing, as you can interpret, because it's a polynomial, so it doesn't really belong to K, right? I mean, this thing is not really in K, but I'm still applying sigma to it. But what does it mean? It just means to replace the coefficients by sigma K, by sigma of the coefficients. Means that is the interpretation you have to take, right? You understand? I mean, it's not strictly in the mathematically, strictly speaking, it is not defined, that expression I wrote, but we understand what it means. Is that fine? Okay. So in the earlier thing, this was just identity. So we were not writing it. Now it has come to the picture. It was there, but we did not see it. You can say like that, right? So now it is there. So you can prove this. And this will help you to solve the other parts of the exercise. Is it fine? Yeah. I hope you also got more intuition as to how this is really working. Okay, it's not just about being able to solve it, but yeah. Like you see, for example, if you look at this psi, the last one, both the things are changing. So you will need that kind of lemma. Okay, right. But please write a proof for, I mean, at least three more of these and send it to me. Okay, gradually then it will become. Yeah. So this calculation is long and not particularly informative, but that should not discourage us from doing it. Okay, so it's fine. Easier ways to determine when an extension is Galois. Right. Fine. So let's see if you have any questions right now about this, whatever we have talked about and so on. Okay. You will find these kind of questions, you'll find this kind of lemmas in the books, but reading them passively is one thing, but also actively realizing their importance is important. So even though they say the calculation is long and not informative, I believe it's good to do it, right? It's not so long that it cannot be done. Yeah. So what do you feel about Galois theory so far? What are your thoughts so far? Whatever is going on, would, how would you summarize all these things? You should write about these. I mean, I write when I learn something. I write what is going on really. Just to, anyways. I mean, so I mean, yeah. But one should think. Mhm. Mhm. Huh? Yes. Yes. So we are trying to find the structure of the subfields. You could put it like that, right? And how they relate to each other, right? Yeah. Say that. Yeah. So, anyways, it's something that you have to think, and obviously, what you say, I mean, look, that is something which is sort of an overarching theme of Galois theory, you can say. But locally, also, a lot of things are happening, like what you are learning today, right? How to extend these maps, right? How to, I mean, when do you know that a map defined on generators extends to the whole object, right? That kind of intuition you are gaining. How do you ensure that, right? I mean, because this kind of phenomena you see in group theory also, right? So if you have, let's say, so I mean, uh, like for example, if you have, let's say, D3 and S4, then T3 has an element of order 3. T3 is what? I mean, the dihedral group, right? So it has an element of order 3, the rotation, right? If you send that to, let's say, the three cycle, some 1 2 3, that three cycle in S4, and then you take a reflection of D3, you take one of the reflections. There are three reflections also. If you take one of the reflections and send it to one of the transpositions, then do you get a well-defined map from D3? Try it, right? Try it. It's a similar question. Similar question, right? And see, like, if you don't, then where is the problem? So the problem you might see is that these two things in D3, which you started with, these two generators, which you know that one reflection and one rotation is a generator, right? These two things, if you get if you don't have a map, you might see that the reason is that these two generators satisfy a relation, but the image generators which you have sent them to, they don't satisfy those relations. Okay, even though the order of is three, the order there is three because you sent a three, because it's like you did all good in good faith. You sent a cycle, a three cycle to three cycle, you sent a transposition to a transposition, but still it was not enough. It was not, it was maybe, or maybe it is correct. You see, this is a similar question, right? It relates to so many other things. I mean, it goes on and on. So you should formulate these things. I mean, obviously, I mean, that what you said, of course, we're looking for that. But that's a big thing. I mean, right? I don't think, and we are not, the intuition probably is not there for that yet. Okay. I don't know. So it's good if it is there. It should be, because I mean, Galois theory you're reading. But you understand, right? These are all these simple things which are also very important. Okay, so then if there is no question, let's move to the next question, right? Let's move to the next question. So let me not do these. Oh yeah, so this is actually an exercise kind of. These things are actually there in the exercises. Next exercises. Okay, this kind of things which I said. Just a minute. Yeah, so there are these things about function fields that. So there is problem number 14. Let K be a field and Kx be the rational function field in one variable. Okay, U be in capital K. Show that Ku is equal to K if and only if U is equal to this for some ABCD with determinant not equal to 0. Yeah, let's do this. This is, I think, yeah, but this is just a problem in field theory. Yeah. Let u equal to, sure. Okay. So this problem statement is very straightforward. The statement is straightforward. So is this fine? Yeah. So this is easy, right? I mean, this I've only written one direction, which is very easy. This direction is very easy. Why? Because so if you, I'll just write this kind of a hint. Okay, that you have to just consider. You have to just go from u to x, right? Somehow you have to construct a rational polynomial in u, which gives you x, right? So you have to do fu by gu, and somehow you have to find x. You have to find f and g. You see that then you will be done, right? Because if you can get x, then you can get everything. Okay, how you will get it? Uh, you don't have to think much in this case because this is already given that it's invertible. So you have to just apply this. Yeah, you have to. You have to still prove a few things. You have to prove a few things. Yeah. What kind of things you have to prove that you think? Okay. Let me. It's not. I mean, you don't know because this is not like how linear transformations work, right? This is not exactly like linear transformations, right? If you say that like this thing, right? But this, I mean, does this make sense from a linear algebra perspective directly? No, but you have to interpret it. Yeah, right. You have to interpret it. Then it will make sense, and then all the rules will be true. So these are called fractional linear transformations. Okay. So yeah, but you can do this point. So I'll leave this part. Okay, I'll go to the next part. So show that kx equals to kv if v is equal to u for some, yeah, v is equal to u as above. Let of course I should say initially that let v be in this, right? So you're choosing some rational function, and from there you want to take rational functions of those rational functions. You see, right? You're choosing v to be a rational function, and then you're taking the rational functions of that. So, for example, just to give an example, you may choose v to be x square by 1 plus x. Correct. Then what will kv be? Right. It will be polynomials in that, or rather, yeah, like rational functions in that, where whatever p and q are in, like this. That's what kv means by definition. So now you have to show basically that it's linear. Okay. So that is a challenge. You have to show that f and g are linear. Yeah, it should not be difficult. It looks true, isn't it? That if it is not linear, then you can't get the other polynomials. You can't get the linear polynomials. Something like that, right? Like if v is equal to x square, then how will you ever get x? Is that correct? Hello? Yes. Do you see the point? If v was equal to x square, I'm saying that what is the intuition? Do you see the intuition why you would make this claim, right? If v was equal to x square, then can you ever get x? Seems no, right? That's the point, right? I mean, if v was equal to x square, then if you do px square by qx square, how will you get x? I mean, you can just prove that this is not possible by something, but multiply, cross multiply, you can prove this, right? So that's why that's why this claim is very natural. Okay, that this is the claim. But yeah, I don't know how to prove this. It should be difficult, but because a little bit out of time, think about it maybe. Okay, it's 1.15, so you have to go to chapter 1 and look at there. There are some examples and some things there. Okay. Okay, I mean, I've actually done this problem before. It was there in Dummit and Foot, I remember. But yeah, because we are out of time, so that's why I will not think because I get late for because they have college, so get late for it. Okay, yeah. So you can think about it, right? You have done one side of it, yeah. So overall, tell me how many questions have you done? 7. Oh, good. Okay. Look, I'm just asking, I mean, because see, the exact numbers are not the most important thing. Most important thing, I understand that. That's not a problem. But the reason I'm asking is just to keep, just to ask, that's my job, right? Okay. So it's not in that sense, but you should write and keep sending to me the work that I'm giving you.